All right, this video is going to go over pages 19 through 22 in your sound and light packet. So we're going to start off with light here. So light is a very small, let me actually switch to my pen real quick, a very small range of frequencies on the EMR scale that we can actually see. That's why it's called visible light. Okay, so the light you see is called white light. So white light is made up of all your colors, so Roy G. Biv. Okay, so you can see your EMR spectrum here. So you start off with radio and go all the way to gamma. So remember, these are all electromagnetic waves. So if we mention these at all in problems, they all travel at the speed of light. Okay, so there's no difference in any of their velocities. Okay, their wavelength and frequencies can be different, but velocities are the same. So as you can see here, as frequency goes up, temperature goes up as well. So the frequency is a direct relation with energy. That's why gamma is so dangerous, because of the frequency. Now, light, the range of frequencies of the electromagnetic waves that stimulates the retina of the eye. Okay, so we see objects because light is either emitted, so meaning coming from the source, or it's reflected by it. So the way you actually see color, like if you see someone with a red shirt, what happens is your shirt absorbs that white light and apparently only reflects the red. It absorbs all the other colors, but reflects the red, so that's why you see it as red. Okay, so if you see a white t-shirt, that means it's reflecting all of the colors, so nothing's being absorbed. So that's why white shirts are typically cooler than dark shirts, because it's reflecting more, so nothing's really coming out, or nothing's really being absorbed. Okay, versus a black shirt means there is no color being reflected, so that means it's all being absorbed. So all those colors are being absorbed, okay, which adds to more energy, which adds to more heat. Now, so we said EMR waves all travel at the speed of light, so this is your actual speed of light, but that's a very fun number to deal with, so we're just going to stick with a 3.00 times 10 to the 8th. So polarization, so if you have polarized sunglasses, this is basically how it works. So if you see here, light is a transverse wave, and it's in multiple axes in all directions. So what polarized sunglasses do is they basically have a little opening, in this case a little vertical opening, that only allows in waves that are in that direction. Okay, so anything vertical will make it through, but anything horizontal or at an angle and stuff will be blocked out. So that's the purpose of them, is because light can be damaging to the eye. So when you have polarized sunglasses, okay, it blocks out a lot of those waves, which reduces the amount of frequency that's coming in your eye, which reduces the energy, which reduces the damage. Okay, so now if you were to take another pair of sunglasses and turn it perpendicular, so let's say this is your first pair of sunglasses. If you take another pair of sunglasses and turn them perpendicular and put the two lenses back to back, okay, what happens is you have the vertical ones that are allowed through, but now you have a horizontal opening, okay, on that second pair. And since you only let in the vertical, now the vertical is going to be blocked out because it's not horizontal. Okay, so that's actually how you can test polarized sunglasses. If you put them perpendicular to each other, it shouldn't let any light through at all, because it blocks out all the different directions. Okay, so that is polarization. Okay, so it is basically because light are transverse waves. Okay, polarization refers to only allowing the wave vibration to occur along one direction. Okay, dispersion of light. So dispersion of light, this looks like that Pink Floyd album, is basically each color has its own angle that it will bend at. So what happens is you have white light comes in. Okay, so we're going to say this is air. Okay, so remember, white light's made up of all the colors. We can't see them because it's all together. But what's going to happen is it hits another medium. So this is refraction. So remember, when you hit a different medium, it causes that light to bend. Now each of those colors are going to bend at their own angle, which is going to separate them. So that's how you can actually see color. Okay, so whenever it rains, okay, you see rainbows outside. That's because what happens is you typically see it after it rains, because there's moisture in the air. So white light is hitting that water that's in the air. It causes it to bend, and therefore it separates that white light into different colors. And so that's how you're able to see that rainbow. Now, a light year. Okay, so a light year is the distance traveled by light in 1 year. Okay, so it's actually a unit of distance. Okay, so what we're going to do is we're going to show you how they figure out what a light year is. So your velocity is going to be the speed of light, which is c. Now your time, we're not going to use 1 year, because remember, our velocity is in meters per second. So we need to figure out how many seconds are there in 1 year. Well, if you take 365 days and multiply that by 24 hours, and then multiply that by 60 minutes, because there's 60 minutes in 1 hour. You multiply that by 60 seconds. Okay, what you're going to get is you get 31,536,000 seconds. So that's how many seconds are in a year. So we're going to figure out how far does it actually travel in 1 year. So we're looking for distance. So we're going to take our velocity, 3 times 10 to the 8th, and multiply that by the 31,536,000. That means light will travel at 9.46 times 10 to the 15th meters in that 1 year. Okay, so that is a light year right here. So this is 1 light year. Okay, so how many light years are in 9.46 times 10 to the 30? So what I'm going to do is I'm going to take 9.46 times 10 to the 30 meters. Okay, so that's how far it traveled. We're just going to figure out how many light years is that. So we're going to divide it by what 1 light year is. So 9.46 times 10 to the 15th. Okay, this is, so before you, if you try to do mental math here, it's not going to be 2. Okay, that whole exponent thing is different rules. Okay, so make sure you use parentheses when you put in the calculator. Okay, so we still see errors with that. So divide those two and you actually get 1 times 10 to the 15th light years. So that is actually quite a few light years. Now, how many light years did a photon travel if it was traveling in a vacuum for 1 hour? Okay, so a photon, so we're talking about everything here is moving at light speed. So a photon here is moving at light speed. Okay, so for 1 hour, so 1 hour doesn't do me any good. I need seconds there. So if you take 60 minutes, or in 1 minute, so 60 minutes times 60 seconds, okay, you get a time of 3,600 seconds. So we're going to figure out how far does this photon travel in that time. So our distance equals velocity times time. So 3 times 10 to the 8th. We're going to multiply that by our time, which is 3,600. And we get a distance of 1.08 times 10 to the 12th meters. Now, that's not my answer. That's just how far it traveled in that time. I want to figure out how many light years is it. So what I'm going to do is I'm going to divide it by whatever 1 light year is, which is 9.46 times 10 to the 15th. And we're going to get 1.14 times 10 to the negative 4 light years, which should make sense because it's smaller. Okay, so it hadn't even reached 1 light year yet. Okay, so that's why it's a small value. So it's not even a full light year. Now, how many light years did a photon travel if it was traveling in a vacuum for 475 hours? So we're going to take 475, multiply that by 60 minutes, and then multiply that by 60 seconds. And that's going to get us a time of 1,710,000 seconds. Okay, so we're going to do the same thing. So distance equals 3 times 10 to the 8th. And we're going to multiply that by that 1,710,000 seconds. And we're going to get a distance of 5.13 times 10 to the 14th. So that's how far it traveled in that time. But that's not light years, so I'm going to divide it by 1 light year. So 9.46 times 10 to the 15th. If you notice now, that light year is staying constant. And you get 0.054 light years. Okay, so closer, but still not a full light year. And so that'd be your answer there. Now, law of reflection. Okay, so law of reflection here, this is just stating that you have an incident angle. So this is your incident angle or incident ray coming in. And you're going to have a reflected ray going out. So this is your reflected. So in the diagram, the ray of light approaching the mirror is known as the incident ray. So that is your I. Okay, the ray of light that leaves the mirror is known as a reflected ray. That's the capital R. At the point of incidence where the ray strikes the mirror, a line can be drawn perpendicular to the surface of the mirror. This is known as the normal line. So right here, okay, that is your end. So that's basically how it helps us determine the angle it comes in at and what it leaves at. The normal line divides the angle between the incident ray and the reflected ray into 2 equal angles. That means your incident angle is equal to your reflected angle. So if you come in at 30 degrees, so let's say that's your incident, that means your reflected is going to be 30 degrees. Okay, so those are both going to be the same. Now the angle between the incident ray and the normal ray is known as angle of incidence. That's what it's talking about right here. So that is that theta I. So remember, theta just means angle. And then the one that reflects off, that is your theta R. Okay, so I'm not going to worry about the whole Greek letter theta thing. So again, that symbol just means angle. Now, the law of reflection states that when a ray of light reflects off a surface, the angle of incidence is equal to the angle of reflection. Okay, so I just really understand that it's simple, okay, but I would know that whatever it comes in at, okay, that is going to be what it leaves at as reflected. Okay, so just make sure you understand that before we get into the whole refracted part where it goes through to a new medium. So that'll end that one.